In the depths of space, where starlight barely pierces the darkness, forces lie hidden that can push the boundaries of understanding. These are objects whose energy can outshine an entire galaxy all at once. Imagine a source that shines brighter than trillions of suns combined, and yet this source is compressed into a point smaller than the solar system. We are talking about quasars and supermassive black holes, entities that have shaped the universe over billions of years and continue to challenge the laws of physics. When astronomers first discovered quasars in the mid-20th century, they were stunned. Small, point-like objects, yet with radiation that could eclipse entire galaxies. How could such a tiny region of space not merely emit light, but literally tear the fabric of the universe with its brilliance? The answer was hidden in the heart of the quasar, a supermassive black hole consuming matter at an incredible rate. This black hole does not simply absorb, it devours, tearing gas clouds and stellar material into the smallest particles. In the process, enormous accretion disks form, heated to millions of degrees, radiating energy in the form of X-rays and gamma rays. Every atom that falls inward becomes part of a spectacle the entire cosmos can witness. We see light born under extreme conditions, traveling billions of light years before reaching our telescopes. And here begins the most intriguing part. These quasars are not merely lanterns in the dark. They shape the fates of entire galaxies. The most powerful among them can launch jets directed across thousands of light years, striking intergalactic gas, suppressing or stimulating star formation. They are like conductors, governing the birth and death of stars and sculpting the structure of galaxy clusters. But how do such tiny objects command all this power? Scientists believe the mass of these black holes can reach billions, sometimes even tens of billions, of solar masses. And the greater the mass, the greater the energy they can release. At first glance, this seems paradoxical. How can a small point be the source of such might? The answer lies in the physics of accretion and in how matter behaves near the event horizon, the boundary from which not even light can escape. It is here, in these extreme conditions, that all the beauty and terror of the universe is revealed. We observe processes that cannot be reproduced on Earth. Temperatures, speeds, and gravitational forces exceed everything we know. Each particle falling into the accretion disk transforms into a storm of light, into energy capable of dispersing intergalactic gas, stimulating new generations of stars, or, conversely, suppressing their birth. The energy of a quasar can be so immense that if one were placed at the center of our galaxy, it would outshine every star in the Milky Way simultaneously. But these objects reside at incredible distances, billions of light years away, and when we observe them today, we are not seeing the present but the past, an echo of the universe's first billion years. Every photograph, every spectrum is a window into an era when galaxies were forming, colliding, and evolving under the influence of these cosmic titans. But the deeper we look into quasars, the stronger the feeling grows that we are not merely seeing bright objects, we are witnessing the fundamental mechanisms upon which the universe itself is built. And among these cosmic beacons are some whose power literally shatters our conventional sense of what is possible. One of them is 3C273, the first quasar ever identified. It lies more than 2 billion light-years from us, yet even from that distance it can be detected through a telescope as a bright point. This means its luminosity surpasses that of hundreds of billions of stars. And this is only the beginning. Modern observations have revealed quasars whose energy is so immense it is difficult to describe in ordinary terms. For example, TIL N618 is one of the most powerful known quasars. At its center lies a supermassive black hole with a mass approximately 66 billion times that of the Sun. To grasp this, one must imagine an object whose gravity is so strong that it governs the motion of matter on scales comparable to entire galaxies. But the true mystery is not in the size. The mystery is in how these objects manage to form at all. We see quasars in the early universe, when it was less than 1 billion years old. This means supermassive black holes grew to colossal sizes in an incredibly short time. And here science encounters one of the sharpest puzzles in modern astrophysics. Standard growth models simply cannot account for such speed. Perhaps the first black holes were born already massive. Perhaps they formed from the collapse of enormous clouds of primordial gas. Or perhaps we still do not understand a key mechanism that accelerates their growth. Some hypotheses propose the existence of so-called direct collapses, in which vast gas clouds bypass the stellar stage and become black holes immediately. But even if that is so, another question remains: why do quasars shine so brilliantly? One might think a black hole should be absolutely dark. Yet it is the very process of consuming matter that makes it one of the brightest objects in the universe. As material spirals into the accretion disk, it accelerates to speeds approaching that of light. Friction, magnetic fields, and gravity heat it to extreme temperatures, transforming it into plasma that radiates a colossal amount of energy. And here an effect arises that cannot be overstated. The efficiency of this process can reach tens of percent, meaning a substantial fraction of mass is converted directly into energy. By comparison, nuclear reactions inside stars convert less than 1% of mass into energy. Quasars are machines operating near the very limits set by physics itself. But there is yet another element that makes quasars truly awe-inspiring: their jets. Narrow, directed streams of particles ejected from the vicinity of the black hole at nearly the speed of light, these jets can extend hundreds of thousands of light years. They pierce the interstellar medium, heat gas, and can literally blow matter out of a galaxy. This means a quasar can halt the birth of new stars by stripping the galaxy of its fuel. This is precisely why scientists believe quasars are not merely bright objects, but a key mechanism of galactic evolution. Without them, the universe would look entirely different. Galaxies might be far more massive, with endless star formation. Or they might be chaotic and unstable. But the most unsettling discovery is that quasars can switch on and off. Yes, these cosmic giants are not always active. They pass through phases of intense activity and periods of relative quiet. This means that at the center of almost every large galaxy, sleeping monster may lurk, one that could awaken at any moment. At the center of our own Milky Way also lies a supermassive black hole, Sagittarius A-. Today it is relatively calm, but there is evidence that in the past it may have been far more active. Enormous structures known as the Fermi bubbles, stretching tens of thousands of light years above and below the galactic center, point to powerful energy outbursts that occurred millions of years ago. This means even our galaxy may have passed through a quasar-like phase. And if it happened once, what would prevent it from happening again? This question compels scientists to view quasars not only as distant objects, but as a key to understanding the future of our own galaxy. Because in studying them, we are in effect studying the possible fate of the Milky Way. And the more we learn, the clearer it becomes, quasars are not simply rare anomalies. They are a phase in the life of galaxies. A phase through which, perhaps, every one of them passes. Which means that somewhere in the depths of space, new quasars are igniting right now. New sources of light that will alter the structure of the universe for billions of years to come. And we are only beginning to understand just how vast that really is. But there is an even stranger effect that makes quasars not merely bright objects, but genuine instruments for studying the very structure of space and time. When light from a distant quasar passes through other galaxies, its path is bent. This phenomenon is called gravitational lensing, and it turns quasars into cosmic spotlights, illuminating the invisible. Imagine, between us and a quasar lies a massive galaxy. Its gravity is so powerful that it curves space like a glass lens. As a result, the quasar's light can split into 2, 3, or even form a ring, the so-called Einstein ring. We see one object in several places simultaneously. And this is no illusion. It is the geometry of the universe itself. Through such observations, astronomers can map the distribution of dark matter, that invisible substance which emits no light yet constitutes the majority of a galaxy's mass. Quasars serve as a backdrop against which its influence becomes visible. Without them, many structures of the universe would remain hidden forever. But there is still more. The light of a quasar carries within it information about everything it has passed through. As it travels through clouds of gas, certain wavelengths are absorbed, producing dark lines in the spectrum, a kind of fingerprint of the matter encountered along the way. By analyzing these lines, scientists can literally reconstruct the composition of the universe at different stages in its history. This means quasars are not only sources of energy, but archives of cosmic evolution. Each one preserves the history of billions of years, how galaxies formed, how hydrogen spread through the cosmos, how the first heavy elements appeared. And here the tension reaches a new level. Because the farther we look, the closer we come to the moment when the first quasars ignited. Which means we are approaching the moment when the universe was first beginning to light its earliest fires. Some of the most distant known quasars are observed as they were just a few 100 million years after the Big Bang. For instance, Boola's J1342+0928, an object that existed when the universe was less than 700 million years old, already contained a supermassive black hole with a mass of hundreds of millions of suns. How is this possible? This question quite literally breaks our current cosmological models. For a black hole to grow to such a size, it needs time. A great deal of time. But the early universe simply did not have it. This leads to one of the most radical ideas. Perhaps the first black holes did not arise from stars. Perhaps they appeared directly, as primordial structures formed immediately after the birth of the universe. Some scientists even consider the hypothesis of so-called primordial black holes arising from quantum fluctuations in the very first moments after the Big Bang. If this is true, then quasars are not merely a stage in galactic evolution. They are a direct window into the moment of the cosmos's own birth. And the deeper we dive into this subject, the stronger the sense grows that quasars are not a side effect of the universe, but one of its fundamental mechanisms. And if quasars are indeed a fundamental mechanism of the universe, then it is logical to ask the next question: what exactly happens at the very center of this process, where matter ceases to be familiar and the laws of physics begin to operate at the absolute limits of their validity? To understand this, we must approach a boundary that cannot be crossed back: the event horizon. This is the region around a black hole where the escape velocity exceeds the speed of light. Everything that crosses this boundary vanishes forever for any outside observer. But the paradox is that for the falling object itself, things look entirely different. Here, general relativity enters the picture. According to it, gravity is not a force in the conventional sense, but a curvature of space-time. And near a supermassive black hole, this curvature becomes extreme. Time begins to behave strangely. Observed from the outside, everything approaching the event horizon appears to slow down. Light stretches, shifts toward the red end of the spectrum, and gradually fades. An object seems to freeze at the boundary. But from the object's own perspective, time passes normally. It crosses the event horizon without noticing any precise moment of transition. This means that one and the same reality has two versions, external and internal. And both are simultaneously true. But the real drama unfolds slightly further out, in the accretion disk. There, matter orbits at near-light speeds, collides, heats, and transforms into plasma reaching temperatures of millions and even billions of degrees. Magnetic fields twist and amplify, beginning to play a central role. This is where relativistic jets are born. These narrow streams of particles are ejected from the vicinity of the black hole at nearly the speed of light. Their origin is not yet fully understood, but one of the leading models, the Blandford-Znajek mechanism, suggests that a rotating black hole literally extracts energy from its own spin through magnetic fields. This sounds like science fiction, but the calculations show it is possible. Jets can extend hundreds of thousands, sometimes even millions, of light years. They pierce the intergalactic medium like laser beams on a cosmic scale. And if such a jet is directed toward Earth, we observe a special type of quasar called the blazar, one of the brightest and most variable objects in the universe. And here another genuinely unsettling moment arises. The energy carried by these jets is capable of more than merely heating gas. It can completely transform the structure of a galaxy. Jets blow out matter, depriving the galaxy of the building material needed to form new stars. This is a process astronomers call feedback. A quasar does not simply live inside a galaxy, it regulates the galaxy's fate. Sometimes, it destroys its future. But even this is not the extreme. In some cases, so-called superluminal motions are observed. When jets are directed almost precisely toward us, the effects of special relativity create the illusion that particles are moving faster than light. Of course, this is an optical effect, but it illustrates just how extreme the speeds and energies in these systems truly are. And now imagine the impossible. What would happen if a person found themselves near such an object? At a safe distance, you would see a blazing disk, brighter than any star, with streams of energy tearing out into the cosmos. But as you drew closer, the scene would begin to distort. Stars behind the black hole would stretch into arcs of light. Space itself would visibly bend before your eyes. And then would begin what physicists call spaghettification. The gravity near a black hole is so uneven that the difference in gravitational pull between your head and your feet becomes immense. You are stretched like a thread, torn apart at the atomic level. And all of this occurs long before you reach the event horizon, at least in the case of smaller black holes. But with supermassive black holes, those that power quasars, the situation is even stranger. Their event horizon is so vast that you could cross it without feeling any immediate destruction. Only deeper inside would the truly extreme processes begin. But what is there, inside? This is one of the greatest open questions in modern physics. At the center of a black hole, according to the equations, there should be a singularity, a point of infinite density and zero volume. A place where our laws cease to function. This is where science reaches its own boundary. Because to understand what happens inside, we need a theory that unites gravity and quantum mechanics. A theory of everything. But such a theory does not yet exist. And this means that quasars, for all our knowledge, remain a mystery. We can measure their light, analyze spectra, observe jets, and model processes. But at the very heart of these objects lies something we are not yet capable of describing. And perhaps it is precisely there that the answer is hidden, not only to the question of quasars, but to the question of the nature of reality itself. And here the narrative takes a sharp turn, from distant, almost abstract science to a question that sounds far more personal. What if one of these cosmic energy sources were aimed directly at us? At first glance, this seems unlikely. Quasars lie at colossal distances. Their light travels to us over billions of years. But the very nature of their radiation makes the situation far more complex. For we are speaking not merely of light, but of directed streams of energy. Jets that can act as cosmic spotlights, boring through space across enormous distances. When such a jet is aimed precisely toward an observer, we call that object a blazar. And its brightness increases dramatically due to relativistic effects. But behind that brightness lies something more dangerous, concentrated energy capable of acting on the interstellar medium. Fortunately, there is no active quasar in our galaxy directing a jet at Earth. The central black hole, Sagittarius A-, is currently in a relatively calm state. But astronomical data suggests that in the past, things may have been very different. The enormous structures known as the Fermi bubbles extend tens of thousands of light years above and below the center of the Milky Way. They are the remnants of a powerful energy outburst that occurred millions of years ago, a kind of scar on the body of the galaxy, evidence that even our own black hole is capable of awakening. And if it has already happened once, it can happen again. But even imagining the worst-case scenario, it is important to understand the scales involved. For a quasar's jet to have a destructive effect on Earth, it would have to be aimed precisely at us and located relatively nearby by cosmic standards. Such coincidences are extremely rare. The universe is vast, and its distances are our best protection. Nevertheless, there are events that demonstrate just how powerful cosmic energy can be. One such example is GRB 221009A, a gamma-ray burst recorded in 2022 that became one of the brightest ever observed. Its energy was so great that it affected the upper layers of Earth's atmosphere despite the enormous distance to its source. This was not a quasar, but the result of a massive star collapsing. Yet it vividly demonstrates that the cosmos is capable of transmitting energy across intergalactic distances with devastating force. And here another important detail emerges. Quasars and gamma-ray bursts are different phenomena, but they share something in common. Both show that energy in the universe can be not merely large, it can be directed. And directed energy is always potentially more dangerous. But there is another side to this story. That same energy which can destroy plays a crucial role in shaping the universe. Without the powerful outbursts of quasars, intergalactic gas would not be distributed as we observe it today. Without them, galaxies might grow uncontrollably, becoming unstable and chaotic. This means quasars are simultaneously creators and destroyers. They can suppress star formation, or, on the contrary, trigger it, compressing gas clouds with shock waves. They balance the system, maintaining a fragile equilibrium between chaos and structure. And the more we study these processes, the clearer it becomes. The universe does not simply exist, it regulates itself. But there is one aspect that continues to generate debate among scientists. How strongly do quasars influence the large-scale structure of the cosmos? Can they determine the shape of galaxy clusters? Or is their influence limited to local scales? The answer to this question is gradually coming into focus thanks to new observations. Modern telescopes allow us to see not only the quasars themselves, but the environment surrounding them. We are beginning to notice how their energy spreads across hundreds of thousands of light years, interacting with gas and dark matter. And this changes the picture. Quasars cease to be point-like objects. They become centers of influence, nodes through which the energy flows that shapes the cosmic web. They are like engines powering the evolution of the universe's structure. And if we look at this more broadly, an almost philosophical question arises. What if, without quasars, the universe could never have come to look the way we see it today? What if these brilliantly bright, destructive, and at the same time creative objects are not a side effect, but a necessary stage? And if that is so, then every galaxy, including our own, carries within it the potential to become something far more powerful and dangerous than we are accustomed to believe.